You selected answer D, which is not correct in this case. And to see why, we can do a simple material balance on component A, where the molar flow rate of A entering the reactor minus the molar flow rate of A exiting the reactor is equal to the volume of the reactor times the rate with which A is consumed, that I'm denoting with a negative so that the amount consumed becomes a positive number. Now the reaction is given as being second order in terms of the concentration of A based on our previous discussion. And we can express the molar flow rates in terms of concentrations by factoring out the volumetric flow rate times the concentration of the inlet stream minus the concentration of the outlet stream, using the fact that for this liquid phase reaction, we don't expect the fluid density to change very much, and so the volumetric flow rate should remain constant from the inlet to the outlet. We can rearrange terms from this expression to isolate the concentrations on the left side and some other terms on the right-hand side. And what we know in this problem statement is that the volume is going to go up by a factor of 2, but we don't expect the rate constant to change because the temperature is constant. We say that the feed conditions are all the same and it's isothermal. And the volumetric flow rate is also not changing because that is one of the feed conditions, is the entering flow rate of species. And therefore, the entire right-hand side of this equation goes up by a factor of 2 when the volume is doubled. Now, that change in a factor of 2 is going to have to cause the concentration to change. And furthermore, we say that the concentration of A has to go down, because when the concentration of A goes down, because it's being subtracted in the numerator, that makes the value of the numerator go up, and it also makes the value of the denominator go down, which makes the total quantity on the left-hand side go up, whereas the converse would be true if the concentration of A went up, and we couldn't have a number that would increase by a factor of 2. Now, since the concentration of A goes down, that means the molar flow rate of A has to go down, since the volumetric flow rate is fixed at this value V0, based on the stoichiometry that if we are having less A exit the reactor for the same feed, right, that means that we have to have more B, so more of the A has been converted, and so the molar flow rate of B has to have gone up, and so it's greater than 2 moles per minute, and answer D cannot be correct.